We've learned a lot about OpenGL and 3D programming, and now we're going to put it all to use. We are going to make a 3D game. And as a matter of fact, we're making this 3D game. If I press enter to start a new game, you can see that it's basically a four-way Pong game. And the paddles are 3D crabs. I'm controlling the crab at the bottom using the left and right keys, and the other three crabs are controlled by the computer using a bit of AI. And this is the game that we're going to be making. We're going to separate the game into two basic components. First, the gameplay, and second, the 3D drawing. So the gameplay will be in game.h and game.cpp. The drawing will be in gamedrawer.h and gamedrawer.cpp. So first we're going to go through game.h. And there's a comment near the top which describes a little bit about the gameplay stuff, so I'll just read it. The game board is a square with corners 0, 0, 0, 1, 1, 0, and 1, 1 in the XZ plane. There are balls and 4 crabs, paddles, in the game board. There is one crab of crab length at each edge of the square. Each crab other than the first, the one on the edge connecting 0, 0 and 1, 0, is controlled by the computer. A player is scored on when a ball reaches the player's side, but the crab isn't there to block it. When a player is scored on, he loses a point. When a player reaches 0 points, he's eliminated, and the side where his crab was turns into a wall. There are 4 circles of radius barrier size centered at the corners that limit balls and crabs' positions. There may be multiple balls in play at once. New balls are added to play by fading in at the center of the board. As in the original Pong, the direction of the ball after hitting a crab depends on the place where the ball hit the crab. So now let's go through some of the code. We have the crab length and barrier size constants up here at the top. Then we have the crab class. Inside the crab class we have the maximum speed field, which is just the maximum speed of the crab in units per second. Then we have this pose 0 field, and I'm calling it pose 0 instead of pose in order to distinguish it from this pose method we'll see later. So pose 0 is basically just the distance from the center of the crab to the corner on its right. And it'll always be between 0 and 1, although it won't be able to reach 0 and 1 because of the length of the crab and because of the barriers. Then we have this dir 0 field, which basically indicates the direction the crab is going. If it's -1, the crab is going towards the corner on its right. If it's 1, it's going towards the other corner. And if it's 0, the crab is just slowing down. Then we have speed 0, which is the velocity of the crab. So if it's negative, then it's going towards the corner on its right. And if it's positive, then it's moving towards the other corner. Then we have this time until next step variable, which is basically the amount of time until we're next going to call the step method. The step method advances the state of the crab by a short amount of time. Then we have the constructor, which takes the maximum speed of the crab as a parameter. We have methods for returning the position, the direction, the speed, and the acceleration of a crab. And actually this acceleration is the acceleration of the crab when it's moving, when it's accelerating or decelerating, I mean. So it may not be the current acceleration. Then we have a function for setting the direction the crab is moving. So if this dir1 parameter is negative, then it'll set the crab to accelerate towards the corner on its right. If it's positive, it'll set it to accelerate towards the corner on its left. And if it's 0, it'll set it to slow down. Then we have this advance method, which advances the state of the crab by a particular amount of time. After that is the ball class, which has fields for the radius of the ball, the position of the ball, and the angle at which the ball is moving. This angle will be 0 if the ball is moving in the positive x direction, and pi over 2 if it's moving in the positive z direction. And this field will always be between 0 and 2 pi. Then we have the fade amount 0 field, which is the amount that the ball is faded in. So usually it'll be 1, but if the ball is fading in or out, then it'll be some fraction between 0 and 1. After that we have the is fading out 0 field, which is whether the ball is fading out. Then we have some methods. We have the constructor, which takes the radius of the ball, the position of the ball, and the angle at which the ball is moving. And the ball will initially be fading in. Then we have methods for returning the radius of the ball, the position of the ball, the angle at which the ball is moving, We have a method for setting the angle at which the ball is moving. We have a method that returns the amount that the ball is faded in. Then we have a method for making the ball fade out. We have a method for returning whether the ball is fading out, and a method for advancing the position of the ball by a particular amount of time. After that, we have the game class, which is going to store everything we need to know about the game. So we have this crab array, or crab zero array, which basically has the 4 crabs. The first crab will be the one on the edge connecting 0, 0, and 1, 0, so it'll be the human-controlled crab. And then each subsequent crab will be counterclockwise relative to the previous crab. And if any of these elements is null, that means that the crab has been eliminated from play by reaching a score of 0. After that, we have this ball 0 vector, which stores all of the balls. And you'll notice, by the way, that I'm using std : vector rather than just vector. That's because we don't have using namespace std, which you're not supposed to have in a header file. It pollutes the namespace something, I don't know. So we'll just have std : vector. Then we have the scores for the different players. We have the time until next step variable, which is the amount of time until we'll call the game step method. We have the handles collisions method, which is basically the same idea as the handle collisions function in the lesson on collision detection. Then we have the do AI method, which is going to set the direction at which the computer crabs are moving based on a little bit of AI. Then we have the step method, which advances the state of the game by a short amount of time. After that, we have the constructor for game, which takes the maximum speed for the opponent crabs, which can be used to control the difficulty of them, so a higher number will make the computers more difficult. And we also have the starting score of the game. After that, the destructor for the game. Then we have a method which sets the direction at which the human-controlled crab is moving. We have a method which returns the score of a particular player, a method for advancing the state of the game by a particular amount of time, and a method for returning all of the crabs that are in play, and a method for returning all of the balls that are in play. So that's the game class. Now let's go to game.cpp and see how all of these methods are actually implemented. See the code for those methods. So, first of all, we have the pi constant, and we have a bunch of game constants. And, by the way, all of these are wrapped in this nice little namespace thing. And we have this crab step time constant, which is the amount of time by which the crab step method advances the state of the crab. We have time to maximum speed, which is the amount of time that it takes a crab to accelerate from no speed to the maximum speed. Then we have this max crab bounce angle offset variable, which is a mouthful. So basically, if a ball hits the player's crab in the middle of the crab, then the ball will bounce straight up. It'll go straight up. But if it hits the exact left side of that crab, then it'll bounce off at an angle of whatever this constant is. So that's what the constant is, basically. Then we have player maximum speed, which is the maximum speed of the player-controlled crab. We have constants that control the amount of time that it takes for a ball to fade in or fade out. We have a constant for the radius of the balls. We have a constant for the speed of the balls. We have a constant that stores basically the number of balls that are in play under ideal conditions. And then we have a variable, or a constant, which is the amount of time by which the game's step method advances a game. And then we have our trusty old random float function. Next is the constructor for the crab class, which just basically initializes some of the variables in the crab class. Then we have the step method for the crab class. And the first thing we're going to do is accelerate the crab. So this right here is if the crab is accelerating or decelerating, this is the amount by which we want it to accelerate or decelerate. Or rather, this is the amount by which we want to change the speed. And if the direction is not 0, we have some code for either increasing or decreasing the speed as appropriate. And same for if the direction isn't 0, we'll want to decelerate the crab. After that, we have code for moving the crab. So we're just going to increase the position by crab step time times the speed. And if the crab has exceeded one of the barriers, we want to move it back so that it's exactly at the barrier. And after that, we have a method that returns the position of the crab, the direction of the crab, and the speed of the crab. So they just return these different fields that we already have in the crab class. And then we have a method that returns the acceleration of the crab when it's accelerating or decelerating. So that's going to be the maximum speed divided by the amount of time that it takes to reach that maximum speed. After that, we have a method for setting the direction of the crab. So it's just going to change the dir0 field. Then we have the advanced method for crabs, which just calls step the appropriate number of times. Then we have our constructor for the ball class, which just initializes some of the variables for the ball class. We have methods for returning the radius, position, and angle of the ball, which just returns some of the fields that we already have in the ball class. We have a method for setting the angle of the ball, a method for returning the amount by which the ball is faded in, and a method for fading out the ball, which just sets is fading out 0 to true. Then we have a method which returns whether the ball is fading out, and we have a method for advancing the state of the ball. So we're going to advance the position based on the speed and the direction at which the ball is moving. And we're also going to update the fade amount stuff. So if the ball is fading out, we're decreasing the fade amount. If it's fading in, right here, we're going to increase the amount, the fade amount 0 variable. And then if there's no time left over after doing that, then we just return. But otherwise, we're going to adjust the x0 and z0 fields based on the direction of the ball and the speed of the ball. So using a little bit of trigonometry right here. After that, we have the constructor for the game, and what we're going to do is set up the crab 0 array to have new crabs. Unless the starting score happens to be 0, then they'll all just be null. Then we'll set the scores to be equal to the starting score, and we'll set time until next step to be 0. The destructor for the game is going to delete all of the crabs and all of the balls. And now we're going to have a little more freestanding functions in the namespace block. And these are going to be used for collision detection. So we have the intersect circle function, which returns whether the point dx, dz lies within r units of 0, 0. And then we have this collision with circle function, which returns basically whether a ball is intersecting a circle and whether it's moving towards that circle. So in other words, whether we want to have a collision with that circle. And it takes as parameters the distance, or basically the displacement to the center of the circle, the sum of the radius of the ball and the radius of the circle, and then the velocity of the ball. So this just returns whether intersect circle is true, and whether the dot product of the velocity and the displacement is greater than 0. So in other words, whether it's moving towards the circle. After that, we have a reflect method, which this is just some math that will give you the reflection of a ball off of a particular wall. So the wall will be represented with this normal field, normal parameter, which is the normal angle to the wall. And this is the angle at which the ball is moving. And the reflect function will return the resultant angle after it's bounced off of that wall. Now we have a collide with circle function, which is going to cause a ball to basically collide with a circle, so it'll bounce off of the circle. And it takes the ball itself and the position of the circle. So if the ball is fading in or fading out, we don't want to do anything. But otherwise, we find the displacement from the ball to the circle, we find basically the normal angle for the circle. So this is sort of like the wall off of which the ball is bouncing. It's the angle of the circle at the point of contact. Then we have the new ball angle variable, which just is the resultant angle of the ball after this collision. And we're going to make sure that this new ball angle variable lies between 0 and 2 pi, and then we're going to call setAngle to set the angle of the ball after the collision. After that, we have a collision with crab function, which returns whether a ball is collided with a crab based on the position of the ball and the position of the crab. So it's basically just whether the two variables are within crab length over 2 of each other. Then we have collide with crab, which is going to cause a ball to collide with a crab. And what we're going to do is just basically take the straight off angle for the crab. So for the crab on the bottom, this would be the angle that's going directly upward. And then we're going to use the max crab bounce angle offset variable and multiply that by the position of the ball on the crab. So if the ball is on the left side of the crab, then we're going to add this variable. If it's on the right side, we're going to subtract this constant, and if it's somewhere in the middle, it'll be something in between negative this constant and positive this constant, depending on the position. And once we've got this angle, we're just going to make sure that it's between 0 and 2 pi, and we're going to call ball arrow set angle. After that, we actually have the handle collisions method of game, and this is going to call all of these functions that I just showed you. So we're going to go through all of the balls and find out the collisions for the balls. So we have this loop right here that goes through the balls. First of all, we're going to have ball barrier collisions. So that's this loop right here. It's going to go through the 4 barriers using these z and x variables, and it'll check whether there's a collision, and if there is a collision, it'll call collide with circle. Then we have ball-ball collisions, which it's going to go through all the other balls, or rather all of the balls that are later in the ball 0 vector, and it'll check for a collision with those balls using collision with circle, and if there is a collision, it'll just call collide with circle to cause the balls to bounce off of each other. By the way, I should point out that some of these bounces between balls don't look that realistic, and the reason is we kind of want the balls to have a constant speed. We want them to stick with whatever the ball speed is, even after they bounce off of each other. And if, for example, the two balls hit head-on, what would really happen is the balls would just dead stop, but we don't want that to happen, so we're going to settle for a less realistic result, which is they would just reverse direction. Then we have our ball-crab collisions, or ball-pole collisions, which, if a particular crab has been eliminated, then a pole is put in its place, sort of a wall. And we're going to have the crab index and ball pose variables, which are going to store the index of the crab off of which it's bouncing, or pole, and the position of the ball relative to that crab. So in the case of the crab on the bottom, this will be the horizontal position of the ball. So we just do some checks to see if the ball has exceeded one of the boundaries of the board, and then we'll set crab index and ball pose appropriately. And if crab index is greater than or equal to 0, which means that there was a collision, then we're first of all going to see whether there still is a crab at that particular place, rather than just a pole in its place. And if there is a crab, we're going to cause the ball to collide with the crab. Otherwise, we'll cause it to collide with the wall. And that's the handle collisions method. After that, we have we're going to have the code for the AI for the crab. And for that, we're going to need this stop pose function, which basically returns the position at which the crab will stop if it just starts decelerating right now. And it does this just using a little bit of math right here. Now, here's the do AI method where we're going to set the directions of the computer-controlled crabs. So we'll go through all of the computer-controlled crabs, and the AI is going to be relatively straightforward. We're basically going to move the crabs towards the ball that's nearest them. And by nearest, I mean in the vertical direction, in the case of the crab on the top, and the horizontal direction, in the case of the other two crabs. So using this loop right here, we're going to find the closest ball. And closest ball dist is the distance from the closest ball currently to the crab. And target pose is the position of that ball relative to the position of the crab. So we just go through all of the balls, and we find the closest ball right here. Then we're going to see basically whether if the crab stops, it will be in the middle 70% of the crab. So that's what this check is right here. If it would be within the middle 70%, then we'll just have the crab stop. If we didn't do something like this, then the crab would, the computer-controlled crabs would just sort of keep oscillating back and forth to where the ball is, but it would never actually stop where the ball is. So it would have a tough time catching the ball sometimes. So if the crab will stop within the middle 70% of the ball, then we'll just stop it. Otherwise, if the target position is less than the current position, then we'll go towards that target, and if it's greater, we'll go the other direction towards the target. After that, we have the step method for the game class, and what we'll do is we'll just advance the state of the crabs by game step time. We'll advance the state of the balls by game step time. We will handle collisions, and then we want to check to see if any of the balls have scored on a player. So we're going to go through all the balls, and if the ball is completely faded in, that is, if it's not fading in or fading out, then we'll first of all put it into this new balls vector, which is going to store all the balls that aren't going to be removed from doing this loop. So we're going to be removing balls from the ball 0 vector if they're completely faded out. Then we'll see if anyone's been scored on, right here, and if so, we'll find the index of the player that's been scored on. So a player is scored on if the ball has exceeded one of the boundaries of the board. Then if someone was scored on, and we'll also check to make sure that that player hasn't been eliminated yet, then we'll decrease their score, and if their score has been decreased to 0, then we'll delete the crab, and we'll set the element of the crab 0 array to be null. And we'll also cause the ball to fade out. Then we have a check to see if the ball is faded out, and if it is faded out, or if it's not faded out, we're going to add it to the new balls vector. Otherwise, we'll just get rid of the ball. We'll delete it. And then we're setting the balls 0 vector to be this new balls vector, which is the balls that are still in play. After that loop, we're going to check whether the game is over. So we're going to check whether either the player has been eliminated, or all of the opponent crabs have been eliminated. And if the game is over, we're going to, or if the game isn't over, we're going to see if we need to add more balls to the board in order to get it closer to the numBalls constant. So what we're going to do is just go through all the balls that are currently in play and see if the ball fits in the middle. That is, see if the middle doesn't intersect any of the balls that are currently in play. And if it does fit, then we'll add it to the middle. So we're just going to keep doing this until we reach numBalls, or until we can't add any more balls at the middle. And in this else branch, which is if the game is over, we're just going to have all of the balls fade out. And then the last thing we'll do in the game step method is called doAI. After that, we have the setPlayerCrabDir method, which just calls setDir on the first crab if it's not null. We have the score method, which just returns the appropriate element of scores. We have the advance method, which is going to call step the appropriate number of times. The crabs method and the balls method, which just return the crab0 and ball0 fields. And that's game.cpp. Now that we've done all the gameplay stuff, we're going to move on to some of the 3D drawing. And first I'm going to md2model.h because I've actually made a couple of changes to the md2 model class. And we're going to take a look at that. So here are the changes. In the load method for the md2 model class, we're actually going to take a vector of texture file names because we're using 4 different textures for the 4 different crabs. We'll make them different colors using different textures. So I've changed the load method in that way. And the draw method will now take the number of the texture that you want to use, the index of the texture, and it'll also take the animation time. So 0 if you're using the beginning of the animation, or 0.5 if you're at the middle of the animation. And in the md2model.cpp class, there are corresponding changes. So let me just scroll down to these. Or actually, let's see. There's our load method, which I changed it to have the texture file names parameter. So we'll have to go down to where it loads the textures. And we have this nice little loop that goes through all the file names and loads them into a texture IDs vector. That texture IDs vector is right here. So these are the OpenGL IDs of the textures. So this is our new loop for loading in textures. There are a couple of other changes towards the bottom. First of all, we have this new texture num parameter, so we're going to have to call GL bind with the appropriate texture ID. And secondly, I should point out that the way that we had this loop right here before, we were incrementing j from 0 to 2, and in fact, that was causing us to specify the vertices of a polygon in clockwise order. But we're going to be using some backface calling this time around, so we're going to specify the vertices in counterclockwise order just by reducing the loop, making j go from 2 to 0 instead. So those are the changes we've made to the md2 model class. Now let's move on to gamedrawer.h. So in here, we're first of all going to say that there's a game class and an md2 model class just with these 2 lines. We don't actually have to include game.h and md2 model.h to let it know that those classes exist. We can just use these 2 lines of code. And after that we have a game drawer class, which is going to take care of all of the drawing for a particular game. So inside of it there will be a game field. It'll store the game. We'll have the md2 model for the crab. We'll have the ID for a display list, which will be used for displaying the barriers. So we'll see more about that later. We also have a display list for displaying the pole with this particular ID. Let me show you what the poles look like just by running the program. It's these green things right here. Those are poles, and these are what show up whenever a crab has been eliminated from play. So that field will keep track of display list ID for a pole. Then we have IDs indicating the textures used for the sand and for the water. Then we have crab fade amounts, this array right here, which basically indicates the amount that a crab is faded in. And I haven't shown you, but when a crab is eliminated, the crab will basically shrink until it completely disappears. So this crab fade amounts variable will indicate how shrunk the crab is. It'll be between 0 and 1, and it'll usually be 1, but when the crab is being eliminated, it'll be some fraction between 0 and 1. After that, we have this anim times field, which is the animation times for the 4 crabs. We have old crab pose, which is going to keep track of the last known position of the crabs, and it's used for when a crab's eliminated from play. Because if you remember, a crab becomes null if it's eliminated from play, so we don't want to forget where the crab was when we're shrinking him. Then we have this variable, which is used to make the water look like it's traveling forward. So this is the amount that the water has traveled modulo the size of the water texture, each square used for the water texture. Then we have this is game over 0 field, which is whether the game is over. We have waiting for first game, which is true at the beginning. So when I start this program, it's true because it's just waiting for a game to happen. But then once I press enter, it'll be false, and it'll stay at false. After that, we have the player crab dir field, which is the direction that the human-controlled crab is going, which is positive, negative, or 0. Same kind of stuff that we've seen before regarding the crab's direction. We have time until next step, which is the amount of time until we'll next call the game drawer's step method. After that, we have this set game method, a private method which sets the game used by the game drawer class. We have setup barriers, which is going to set up the display list for the 4 barriers. We're actually going to have one display list for displaying all 4 of the barriers. And then we have the setup poll method, which sets up the display list for the polls. We have the step method, which advances the game by a particular amount of time, short amount of time. We have a setup lighting function, which sets up the positions of the lights and the intensities of the lights. We have some methods for drawing different things in the game. So we have draw crabs and poles, which is going to draw the crabs and the poles. And some of these are going to take an isReflected parameter, which is basically whether we're drawing a reflection rather than drawing the objects themselves. And we'll need this because we're going to try to not enable GL normalize whenever possible. But if the object is reflected, then we kind of have to enable GL normalize because because GL normalize, we're only disabling it for when we're not scaling stuff really. Then we have draw barriers, which draws the 4 barriers. We have draw scores, which draws text for the scores. Draw balls, which draws the balls that are in play. And draw reflectable objects, which is basically going to call all of these methods that I just pointed out. And we have draw sand, which draws the sand, draw water, which draws the water, and draw winner, which is going to draw, at the beginning of the game, it draws this instructions text, and then whenever a game is completed, it'll draw some text indicating either that you won or that you lost. And it'll also draw this instructions text. And after that, we have the constructor and the destructor for a game drawer. We have the function that actually draws everything. We have a method that advances the state of the game. We have a method that sets the direction that the human-controlled crab is going. A method that returns whether the game is over currently. And we have a method for starting a new game, given the maximum speed of the computer-controlled crabs and the starting score for the game. After that, we have init game drawer and cleanup game drawer, which are basically just going to be used to call T3D init and T3D cleanup for initializing resources for the text drawing functionality and for freeing those resources when we're done. Now let's go on to GameDrawer.cpp and see the implementation of some of this stuff. We have at the top the pi constant. We have a step time constant, which is the amount of time by which the step method advances the game. We have this walk anim time variable, or constant, which is the amount of time for one particular loop of the walking animation. And you may not have noticed, but these crabs are actually animated. So if you just hold the right key, you'll see the crab sort of continually walking, even though he's at the border. So you can see what this walking animation looks like. And we also have a standing animation, which is for when the crab is not moving. And this is the amount of time of one loop of the standing animation. After that, we have the amount of time that it takes for a crab to completely shrink to nothing when it's been eliminated. And we have a variable, or a constant, indicating the number of points used to approximate a circle when we're drawing the barrier model. We also have the number of points used to approximate a circle when we're drawing the poles, when we're drawing the cylinder for the poles. We have the height of each of the barriers. We have the radius of the poles, and the height of the poles above the ground, that is the height of the center of the poles above the ground. We have this crab offset variable, or constant, which is basically the number of units that the human controlled crab should be translated in the z direction, and also the amount by which we should be translating the other crabs in the appropriate directions. Then we have the water texture time constant, which is the amount of time that it takes the water texture to travel water texture size units. And water texture size is basically the length of each repetition of the water texture. Water alpha is the opacity of the water when we're drawing it. So let me just show you, if you hadn't noticed before, the way that this water is moving forwards continually in our 3D scene. So after that constant, we have the load texture function, which we've seen before. We have the constructor for GameDrawer, which is going to set up some of our variables. So it sets game to be null, the player's crab direction is 0, and it starts a new game with a maximum score of 0, which this is kind of a placeholder game. So technically, when you start the program, the GameDrawer class sort of has a game that's in play, but it's just a placeholder game. It's not really a game. Then you have the amount that the water has traveled, the distance that it's traveled, and now we're going to set up a vector storing the file names for the different textures that we're going to use for the crabs, and then we'll call md2model : load to load in the crab model. Then we're going to call setup barriers and setup pole to set up the display list for the barriers and the display list for the pole. And then we'll load in the sand and water images and store their texture IDs into the sand texture ID and water texture ID fields. Then we have the destructor for the GameDrawer class, which just deletes the game. We have the setGame method, which is a private method of GameDrawer, and if the current game is not null, we'll delete the game. Then we'll set the game field to be this new game. We'll set the player's crab direction to be the last known player crab direction, and we'll set time until next step to be 0. We'll set is game over 0 to be whether the game is over, whether the first player's score is already 0. So this will really only be true at the very beginning, when we're using the placeholder game that has no maximum score. Then we have waiting for first game, which is our variable that's only going to be true at the beginning, before any game has been started. After that, we're going to loop through and set the anim times array to be 0, set all the elements to 0. We're going to set all of the crab fade amounts elements to be 1. Unless the game is over, we'll set them to be 0. Then we're going to set the old crab pose array using the positions of the crabs. After that, we have the setup barriers method, which is going to set up the display list for the barriers. So now we're actually going to see some OpenGL code. So what we're going to do is load in the texture for the barriers, and then we're going to make room for the list for the barriers, the display list for, actually this is a display list for one particular barrier. So our display list for all 4 barriers is going to call the display list for one barrier 4 times. That's the way we're going to do it. So we'll use glNewList to start setting up the display list for the barrier, and We'll enable textures. We'll set the current texture to be that texture that we loaded in at the beginning of this method. Then we'll switch to using blurry texture mapping. And we're actually going to make these barriers be a little shiny. So what we'll do is we'll have this material color array, which is going to be the color of the barrier. And we don't want to mess with the color that's already in the texture, so we'll just set it to be 1, or 111, which is white. And we'll use GL material FV to indicate that color. Then we'll set the normal to be 010 because we're going to draw the face that's pointing up. And we're actually going to use this new thing, GL triangle fan. And let me show you what a triangle fan is like. We're going to be using this to draw the top face of the barrier. So I have a picture in here. So this demonstrates what a triangle fan looks like. So you specify the vertex in the middle and then all these vertices on the outside. And OpenGL will draw triangles connecting the middle vertex and every consecutive pair of the other vertices. So this is how we're going to draw the circle using a triangle fan. So first of all, we specify the vertex in the middle, and then we'll go through all the other vertices, which, just using a little bit of trigonometry, we're going to find the position and texture coordinates of those vertices. And then we'll call GL end when we're done drawing the triangle fan. After that, we're going to draw the bottom circle. So it's the same idea, we're just using another triangle fan. Although in this case, we're not using just a we're not using textures, so we're going to disable textures. And it's the same idea right here. Then we have the cylinder part of the barriers. So we're going to actually use a quad strip, which is another new thing. So let me show that right here. A quad strip is basically where you indicate pairs of points to use for quadrilaterals. So this quad strip thing right here basically could be drawn by indicating the vertices in this order. So we're going to be using a quad strip to draw the cylinder. And we can compute the normals that we're going to be using just based on the ideal normals for the cylinder. And we'll set up the cylinder using a little bit of trigonometry. We'll figure out the points for the cylindrical part. And once we're done drawing the quad strip, we'll call GL end and then GL end list, because we are done drawing the barrier. Now for the barrier's display list, we're going to want to draw 4 copies of the barrier. So we'll just make room for the barrier. We will have a call to GL disable GL color material, because we need to disable color material in order to add a little bit of shininess in order to use these GL material F and GL material FV calls. Then we're going to add some shininess right here using GL material FV and GL material F, and we're going to draw the 4 barriers just by calling the barrier display list 4 times. And once we're done, we'll just re-enable color material, and we'll set up the color and the specularity back to be just white and no specularity. And then GL end list. So we've set up a display list for displaying the 4 barriers. Now we want a display list for displaying the pole. So we'll start our display list, and we'll disable textures, because this is just a colored pole. We'll set the color to be this green color, and then we'll draw the left circle using a triangle fan, draw the right circle using a triangle fan, and then draw the cylindrical part using a quad strip. And all of this stuff is the same idea as for drawing the barriers. Then we have a call to GL end list. Now here's our step method for the game drawer class. we're going to advance the state of the game by the step time. Then we'll advance the water by increasing water texture offset, and then making sure that it lies between 0 and water texture size. Then we're going to go through all of the crabs and update anim times, crab fade amounts, and is game over 0, whether the game is over. So we'll have this opponent alive variable, which is going to store whether we've found an opponent that's still in play, that hasn't been eliminated. And now we'll go through all of the crabs. So if a crab is not null, we'll update old crab pose. Then we'll update the animation time. So what we'll do is if the crab is not removed from play, then we'll just check which direction the crab is going, and if it's just standing, we're going to increase anim times by step time divided by stand anim time. And if it's walking, we're going to change it by step time divided by walk anim time. And we'll either increase it if we're going in the positive direction or decrease it if we're going in the negative direction. So in other words, we'll be running the animation forwards if we want, if the crab is moving in the positive direction, and we'll run the animation backwards if it's moving in the negative direction. After that, we'll just use these loops to make sure that it lies between 0 and 1. Then we have this code right here to update the fade amount for the crabs. So if the crab is null, meaning that it should be fading out, we're going to decrease the crab fade amounts variable, or one element of it, I should say, by step time over crab fade out time. And if it goes below 0, then we're going to set the amount back to 0, and if the player happened to be the first player, which is the human control player, then we're going to say the game is over. We don't want to sit around watching the computer play itself. We just want to end the game whenever the player is eliminated. And if the crab has been faded out completely, or has not been faded out completely, then we're going to set the opponent alive variable to be true if it happens to be a computer opponent. So that's these two lines right here. Then if an opponent is not alive, if no opponent is alive, then we're going to say that the game is over and the player has won. After that, we have the setup lighting function, which sets up the ambient lighting and then goes through each of the 4 corners and sets the lighting for that corner. And it uses a nifty trick where GL light 0 plus 0, for instance, is going to be GL light 0, and GL light 0 plus 1 is guaranteed to be the same as GL light 1. GL light 0 plus 2 is GL light 2, and so on. So using that little trick, we're going to set up 4 lights, which are going to be above the 4 barriers. After that, we have draw crabs and poles, and if the crab model is not null, we're going to do all of this drawing. So we'll enable GL normalize, and then we'll go through the individual crabs. So first of all, we'll translate and rotate to the appropriate side of the board, and if the crab is not null and it's not fading out, or rather it hasn't faded out, then we're going to draw the crab. So we'll find the position of the crab and then translate to it, and if the crab is shrinking, then we're going to shrink the crab and translate it a little bit to make sure that it's still resting on the ground. Then over here, these are sort of my fudge factor functions that basically correct for the fact that I didn't set up the position of the crab in Blender to be correct. So the orientation was a little bit off, the position was a little bit off. So we'll just fix it using these calls to GL rotate F and GL scale F. After that, we're going to call set animation on the crab model, depending on whether the crab is standing or whether it's walking. And we'll call GL color with the color white to make sure there's no color applied to the textures. And we'll draw the crab. and then we'll call GL pop matrix. So that's what we do if the crab is still in play. Now, if the crab has been eliminated, and this counts even if the crab is still shrinking, then we're going to draw a pole where the crab is. So, if this is a reflection of the pole, then we're going to disable GL normalize, and then we'll just call the display list for a pole, and then we'll re-enable GL normalize if this was the reflection. And then we'll call GL pop matrix. So that's how we can draw the crabs and the poles. After that, we're going to have code for drawing the barriers, which just basically either enables or disables GL normalize, depending on whether is reflected is true, and then calls the display list for drawing the 4 barriers. Then we have a function for drawing the text for the scores. So we're going to loop through all of the players, and in this string stream, we're going to get a string that stores the score of the player. So we'll get the string into this str variable. Then we're going to push matrix and translate to the appropriate position. Then, just using a call to t3d draw 3d, we're going to draw the player's score in 3D, and then we'll pop the matrix. After that, we have the draw balls function, which is going to draw the balls, and we're going to either enable or disable GL normalize, depending on whether is reflected is true. We're going to disable textures, disable alpha blending, and we're going to go through all of the balls. So if the ball is fading out, we're going to enable alpha blending, and we're going to give the ball an alpha component of ball arrow fade amount. And otherwise we'll just set the color to be this light gray. Then we're going to push the matrix, we're going to translate to the center of the ball. We're actually going to go a little bit above the center of the ball. We're going to give it a height of 0.01, so that way that the ball is a little bit above the water. It's not resting exactly on the water, because that would sort of bring us the possibility of rounding errors, where just because of a little bit of rounding, the ball might end up a little bit below the water, and then its reflection will end up a little bit above the water. It'll look ugly. So that's why we have this extra 0.01 to the height of the ball. Then using a call to glut solid sphere, we'll draw the ball, and then we'll pop the matrix. And we'll disable blending if we had enabled it. After that, we have draw reflectable objects, which just calls our 4 methods that we just saw: draw crabs and poles, draw barriers, draw scores, and draw balls. Then we have a draw sand method, which is just going to draw a quadrilateral. So again, this sand's a little bit off the ground, or a little bit higher than the water, because we don't want this to be submerged by the water due to some kind of rounding error. Then we enable textures, bind the texture, set up the texture mapping, do all this stuff that we've seen before. Then we have the draw water method, which we're going to disable lighting for this method. So we'll just draw the water as is, draw the water texture, and we'll enable textures, we'll set up the texture, we'll disable GL normalize, we'll enable blending, and we're going to set up the color of the water, and the alpha is going to be this water alpha constant that we've seen earlier. And then we're actually going to draw the water. And the water is going to be a giant quadrilateral that goes really far in all of the directions. So it's going to look like it extends forever, but really it has a limit. And all of this is really the same idea as drawing the ground in the animation lesson that we saw earlier. It's kind of operates the same way. Then we're going to disable blending and re-enable lighting. Now for the draw winner method, where we draw the instructions or the winner if appropriate, well, if the game is not over, then we don't want to draw anything. Otherwise, we're going to set the color to be this blue color, and if the user is not waiting to play the first game, then we know that we just finished the game, so we can draw the winner of the previous game. So we'll store a string indicating who the winner is in this str variable, and then using a call to t3d draw 3d, after some translations, rotations, and scaling, we are going to draw the text indicating who won. After that, we have code for drawing the instructions, and that's just stuff we've seen. It's translation, rotation, and scaling, and a call to g3d draw 3d. By the way, you'll notice that this string for the instructions, it spans multiple lines using this sort of weird syntax. You are allowed to do that in C++. It'll basically interpret all of this as just one string. After that, we have the draw method, which is going to call all of these other methods, and it'll be our main method for drawing everything. So we'll set the background color to be sky blue, which you can't exactly see the background, although you can sort of see it bleed through the alpha blended water a little bit. Kind of hard to notice because it's kind of the same color as the water, but anyway. Then we're going to set the backface culling to cull the front faces, and then draw the reflections. Because when we've scaled all of the objects by -1 in the y direction, we're actually going to switch the vertices to be from being specified in counterclockwise order to being specified in clockwise order. So we need this call to GL cull face GL front in order to cull the correct face. And once we've done that, we'll just scale everything by -1 about the y-axis. We'll set up the lighting and then draw the reflectable objects. So this will draw the reflections of the objects. Then we're going to draw the normal versions of the objects. So we'll set up the lighting and we'll draw the water, which is going to be alpha blended on top of the reflections, and draw the sand, draw the winner of the game and or instructions if appropriate, and then we'll draw the objects that have reflections. By the way, I should point out that we're not using anything with the stencil buffer right here. That's because the stencil buffer was only really useful if our reflections were sort of leaking off the reflecting surface. But if you run the program, you'll notice that actually all of these reflections are already covered by the water quadrilateral. So we don't need to use any stencil buffers in this case. Makes things more convenient, easier. After that, we have this advance method, which advances the state of the game drawer just by calling step some number of times. We have set player crabdir, which sets the player crabdir field and then calls set player crabdir on the game. After that, we have is game over, which returns is game over 0. We have start new game, which just calls set game with the new game with the appropriate parameters. And then we have init game drawer and cleanup game drawer, which, like I said earlier, just call t3d init and t3d cleanup. And that is our game drawer class. Now let's go over to main.cpp. I'll scroll down a bit, and we have a constant for pi. We have timer ms, which is the number of milliseconds between calling update. If the program is running a little bit slowly on your computer, you can just kick this up, and it'll be more choppy, but it'll speed up the game at least. Actually, what we should have done is measure the time every time we call the update function, the timer function. We should have measured the time between the last call to the update function and the current call, and then advance the state of the game by that amount of time. But I decided against that, just to keep things simple. Then we have our game drawer right here. We have variables is left key pressed and is right key pressed, which indicate whether the left key and the right key are currently depressed. And then we have rotation var, which is going to be used to, if I run the program, it'll be used to make the camera angle change a tiny bit over time, which you may or may not notice it, but this scene is sort of rotating clockwise and counterclockwise really slowly. So, like right now, this pole is sort of diagonal, but after a while, the pole will get straight, and then the pole will be diagonal the other direction. So this rotation var is going to let us do that thing. It'll make us be able to have this sort of effect. Now rotation var will start out as 0, and then it'll climb until it gets to 2 pi, and then it'll jump back to 0, and then climb again and jump back to 0 again, and so on. Our cleanup function is going to delete the game drawer and then call cleanup game drawer. In handle key press, if the user presses enter, which is \R, then if the game is currently over, then we'll start a new game. That's what the enter key does. And if the user presses escape, like usual, we'll just call cleanup and then call exit. Now we'll have a handle special key press function, which we'll actually use to handle the left and the right keys. Because the left and the right keys don't have any ASCII equivalents, so we can't just use handle key press to handle them. We have to have a special function. So it's going to take an integer key, and just like handle key press, the coordinates of the mouse. So if this key is glut key left, indicating that the user pressed the left key, then we're going to set is left key pressed to true, and then we're going to call set player crabdir to set to the appropriate direction. And same with the right key, we'll set is right key pressed to true. After that we have a handle special key released function, which will be called every time anytime a special key is released. So we'll use it for when left is released. We'll set is left key pressed to false and then set the direction of the crab. And same for the right key. Set is right key pressed to false and set the direction of the crab. After that, our init rendering function, which sets up all of our stuff and calls init game drawer. So we're going to actually enable backface culling for this because we're using backface culling pretty much throughout our program, throughout the drawing code. Then in our handle resize function, I actually changed the near and the far distances from the usual distances that we've been using in other programs, which are 1 and 200. I've changed it to 0.02 and 0.5 and 5 because our game board is 1 unit long, so we're really only using 1 unit of distance. After that we have the draw scene function, which is going to set up some stuff with the camera. So we'll translate a bit to get the board down and away a little bit, and then we're going to rotate by 50 degrees. So if we were to rotate by 90 degrees, we would actually see an overhead view of the scene. If we rotated by 0 degrees, then you'd see the game head on, which would be pretty hard to play. And we're rotating 50 degrees in between. So it'll make our game look a little 3D without making it unplayable. Then we have a rotation by 180 degrees about the y-axis, which will just make it so that the player's crab is on the bottom rather than on the top. After that, we're going to do that effect that I was saying, where the camera is rotating a tiny bit over time. So we translate to the middle of the board, then we're going to rotate the board about the y-axis, and we'll rotate it by 3 times the sign of this rotation var variable. So this angle will slowly range between, it'll slowly oscillate between -3 and 3 degrees, so that the camera will rotate a little bit over time. And then we'll translate back to the corner of the board. Then we finally call the draw method on the game drawer, and that'll actually draw the game. Now in our update method, we're just going to call advance on the game drawer, and we're going to increase the rotation var variable, and then make sure that it's between 0 and 2 pi. And our main function, there are a couple of new things, just glut special func and glut special up func, which are going to be used for those special key press functions that we saw earlier. So that's our main function. And we have done it! We've made a 3D game using OpenGL.